Hello everyone, this is lecture 3 for the module 4 for computer organization and architecture course. In this lecture I am going to talk about the cache performance measurement and its related parameters like cache miss types, hit ratio calculation, the write policy and the multi-level caches. So, basically the cache memory performance is measured in terms of the how many references generated by the processor found in the cache memory. References are nothing but the data requested by the processor for executing the program. It can be data or it can be instruction as well. It is a combination of instruction and data. So, more the processor references found in the cache, better the performance. In simple way, we call that if reference found in the cache memory, then this event is treated as a hit in the cache. Otherwise, it is called as a miss. And in case of miss, the data has to brought from the main memory to the cache memory, and then the processor can fetch the data from the cache memory and execute the program. So, for every penalty, every miss occurs, a penalty is associated in terms of accessing to memory and via the system bus data transfer from main memory to the cache memory. In case of miss occurs, the data miss occurs means data is not available in the cache memory. So, first the corresponding block of data has to transfer from main memory to the cache memory via the system bus, and that is a slow process compared to the getting the data directly from the cache memory. So, that is a penalty. So, this will take more time. So, if for each miss there is a penalty associated in terms of the time lag between requesting the data by the processor and getting that particular data. So, more hits are there, that will reduce the average access time, and that is our ultimate goal for introducing the cache memory between the processor and the main memory. Average access time is accessing how much time required to access, let us say 100 data are accessed by the processor, data or instruction, then the amount of time required. So, some hits will be there, some misses will be there, for the data is not available in the cache. So, the misses are less, then definitely the average access time will be reduced. Now, the question is what are the type of misses are there? Can we classify these misses? The answer is yes. How to classify the misses? We know that initially cache is empty. Empty means there is no valid data is there. When you start your machine and load your program into the memory, operating system load the program in the memory, main memory, at that time cache is empty, cache have no valid data. Because a digital system, so each cache location contains some information, but that information is a garbage information, it is not a valid data. So, when the program start execution, as I said, your cache is empty or not have any valid data. Now, data will be populated in the cache as processor requests or generate the references corresponding to that program, and then the corresponding data or instruction brought into from main memory to the cache memory. So, initially, irrespective of whatever the size of the cache or whatever the mapping is used, whether it is a associative, set associative or cache direct mapping, all initial few references are always the misses in the cache. So, to indicate this, there is always the line in the cache is looks like. So far we know that whatever the mapping is there, So, you have data is there, then tag also stored along with that, and now we can understand from this one bit that is called as a valid bit is also stored. This is a 1 bit information. 1 bit information that indicates this single bit. If so, let us say if this bit is 1, then I say the valid data is there in the cache. If this bit is 0, then invalid. Otherwise, because in digital system some information will be there in the form of 1010, and the address generated by the processor, let us say that belongs to or that map to one of the cache line, and if some data is already always there. So, in that case, but it is valid or not valid, that is a different issue, but due to this processor can end up the wrong data. So, before accessing or before taking any data or before reading any data from the cache line, first it checks whether the valid bit is 0 or 1. If the valid bit is 1, then only the data will be taken from the cache memory, otherwise it is treated as a miss. So, these type of misses are always there, and it is called as a cold, also called as a cold start misses or the first references misses. Second type of miss is come through with the size of the or capacity of the cache memory. Say for if the to execute any program, we need some minimum number of blocks should be there in the memory. Blocks means the minimum amount of data, some minimum amount of data that is called as a working set, current working set data. If that is not there in the memory, then you can say every alternate reference will be a miss in the cache. So, if your cache size is not enough to accommodate that minimum amount of blocks or that minimum amount of instructions and data combination, then the number of misses will be very high. So, cache size should be enough such that these misses should not occur, misses due to the size of the cache should not occur. So, that kind of misses are called as a capacity misses. In the capacity misses are basically those misses that occur regardless of whatever the associativity or the block size is there. You cannot change the performance if your cache size is not enough, then the performance cannot be improved either by changing the associativity or changing the size of the block, it does not matter. So, first and the important thing is required, that is the cache size should be enough such that it can accommodate the current working set of the program which is going to execute. Third is the conflict misses. Conflict misses, say for example, in the direct mapping, more than one block of the main memory mapped to one cache line, and whenever, so at a time out of these blocks which are mapped to a particular cache line, only one can reside in the main memory, in the cache memory, that particular line. So, if other block which is mapped to the same line is referenced by the processor, the previous has to be removed or it has to be overwritten by the new. So, that situation is called as a conflict. Even some cache lines are still empty or the valid data is not there in these cache lines. These cache lines cannot be utilized because due to this mapping constraint. So, this mapping, this is called as a conflict. So, this conflict can occur in a direct mapping, and this conflict also can occur in SAT associative mapping. Can this conflict occur in fully associative mapping? The answer is no. In fully associative mapping, there is no conflict misses, the misses will occur due to the capacity only. because at one point of time we know that the main memory is far larger than the cache memory, or in other words cache memory is smaller than the main memory. So, at one point of time definitely misses will occur, because the whole data from the main memory cannot be accommodated at one point of time in the cache memory. So, whatever the misses will occur in the fully associative, that will be the capacity misses or the compulsory misses, that is always applicable. The initial few references will always be the misses that is treated as a compulsory misses. Now, we look at how to measure the performance of a 2-level memory system. In 2-level memory system means we have processor is there, this is processor, and 2-level means I have one cache memory. So, that cache memory is directly connected to the processor, dedicated line bus. Then I have a system bus, this is system bus, and through this system bus cache memory is connected to the main memory. Definitely other IO modules are also there, I am not showing here to make the simple. So, this is the way how the 2-level memory operation happens. Processor directly request the data to the cache memory. If data is available, immediately it can provide it to the processor. Not available, in that case, if this data is not available, then the cache memory, the data is transferred from main memory via system bus to the cache memory, and from cache memory it can be provided now. So, that is the 2-level memory operation. So, now the hit ratio is the one of the parameter through that we measure the performance of our memory system. So, how to calculate now hit ratio? So, the formula which is used is to calculate the average access time. The access time, that the total on average access time means some references are found in the cache memory, some references are found in the main memory. Main memory access time is different from the cache memory access time. So, if some references are found in main memory, some in a cache memory, then definitely the average access time will be more than the cache memory and less than the main memory, somewhere in between that. So, here in this formula you can see the average access time Ts can be calculated by, let us say T1 is the access time for the cache memory and H is the hit ratio, number of hits found. Let us say out of 100, let us say 90 reference found in the cache memory. So, 90 times access time will be what? Equal to the cache memory. So, that ratio has to multiply with the access time of the cache memory. Remaining references out of 1 is the total. So, 1 minus whatever the hit are there. If you subtract this, these remaining references are, for remaining references the cache memory and main memory both has to be accessed. So, first cache memory will be accessed, that time is T1, and then the main memory will be accessed, that is T2. So, it is a for the remaining references which did not find in the main cache memory, for their the access time will be T1 plus T2, addition of both cache memory access time plus the main memory access time for these references. So, average if you add it, so 1 minus H multiply T1 plus T2. Here M1 is a cache memory, represent the cache memory higher level or cache memory, and M2 represents the lower level or the main memory. So, that is the average access time. From this formula we can calculate the average access time, or we can, if average access time is given, then we can calculate the hit ratio. What is the hit ratio for the particular memory system? And next parameter for performance is the cost. So, the cost of the overall memory system we want to reduce it, and the performance we want to increase. So, there is a trade off between the cost and the performance in terms of the access time. So, average access time we want to reduce as minimum as possible, and the cost also we want to reduce as minimum as possible, but not on the cost of the performance. Some performance at up to some level performance is required. So, for that we have to our cache size should be enough such that it can accommodate the minimum number of blocks which required to execute a program, and that is different for different programs. That size is not only one size is you can get, because each program have the different level of locality of reference, or the different level in the terms of the amount of data which is at a time which is required. That is always program to program, it varies. So, we need to reach to the conclusion to this size, what is the appropriate size of the cache, through some running or testing the memory system on different set of programs, bunch of programs called as a benchmark programs. So, for the cost formula is average cost. To calculate the average cost, here C1 is a cost for cache memory, S1 is the size of the cache memory, C2 cost of the main memory, and S2 is the size of the main memory, cost per bit here, and S1 plus S2 divided by S1 plus S2 the size of the cache memory and size of the main memory. Through that you will get the cost per bit. Then another parameter which used to measure the performance of the memory system, cache memory system or two level memory system, I say access efficiency. Access efficiency from the same formula which is I showed in the previous slide, average access time. So, T1 is the access time for the cache memory, Ts is the average access time. So, this is average access time and this is the access time for the cache memory, Cm. The ratio of these two, it measures how close the average access time to the M1's access time. M1 memory means cache memory. So, if my average access time is closer to the main cache memory access time, that means more hits are there. Most of the reference is found in the cache memory, then only my average access time can be closer to the cache memory only. So, that is the one of the parameter through that we can find out that the hit ratio is how much the hit ratio, or hit ratio, whether the hit ratio is closer to 1 or it is far away from the 1. Then we have the two options. One is the cache can be provided on the chip itself, in which the processor is there, on chip cache and off chip cache. For the on chip cache, nowadays in the computers we can provide the on chip cache as well, because of the improvement or enhancement in the technology. More number of transistors are available now on the chip. So, some transistors can be used for the implementing the processor logic, including ALU register and all, and the remaining transistors can be used for providing the memory there itself in the chip, and that is always faster. So, compared to the main memory, that on chip cache memory is 25 to 50 times faster, or it is as equal to the processor's speed at which the processor can work. So, if data is available from the cache memory, in the cache memory, on chip cache memory, so that is always processor can get that data at a faster rate. Earlier, because of this transistor density was less, so the number of transistors were not sufficient for providing the cache memory in the processor chip itself. So, that is why the cache memory was outside of the processor, and that is connected directly to the processor, a dedicated bus. So, the off chip, these memories, cache memory access time is 5 to 15 times faster than the main memory. Still it is, access time is very low compared to the main memory, 15 times, 5 to 15 times faster than. So, means processor will get the data 5 to 15 times faster compared to the main memory if data is available in this cache. Now let us look at one example to calculate the hit ratio. So here the cache memory access time is given as 80 nanosecond, main memory access time is 1000 nanosecond, and average access time is also given as a 180 nanosecond. So we need to calculate the hit ratio. So for calculating hit ratio, the average access time formula, let me write. So T average access time equals to H is a hit ratio, let us say. T1 is access time for the cache memory, and the misses are 1 minus H multiply with the access time of main memory plus cache memory. That is the formula we used for calculating the average access time. Now put the values and get the hit ratio. So Ts equals to 180. Hit ratio we don't know, so we keep it as H. T1 is 80, 1 minus H, 80 plus 1000, so it is a 1080. If you solve this equation, you will get 1000 H equals to 900. So H equals to 0.9, or in percentage we can represent by 90%. So here I can say this hit ratio for these memory parameters is 90%. Average access time is given and the individual access time of the memory is also given, then we can find that okay, this is the hit ratio. 90% references are found in the cache memory, remaining 10% references are from the main memory. So here you can see the access time, because this average access time is 180, that is nearer to the cache memory. Cache memory's access time. So means that cache memory system is better. 90%, 90 or more than 90% references are found in the cache memory. That means this system, that kind of memory system is good. Size of the memory or block size or the mapping function or replacement algorithm, all are used as a appropriate sizes or appropriate numbers. So what hit ratio we got? We got hit ratio 90%. Now during the execution of the program, it may be possible that the processor is getting the data, fetching the data from the cache memory, let us say it is available in the cache memory in the case, and then it is processing that data as per the program requirement. Maybe that data is modified. Means now in this case what happened? In the main memory data have the different copy, in the cache memory data have the different copy. And we know the ultimate store of our data is the main memory, because other modules, let us say IO modules are all, they are communicating through the main memory and then they can take the stale copy of the data at that moment if they are accessing. Or in the case when we say that more than one blocks are of the main memory are mapped to the cache memory, that happens in any kind of cache mapping function, or at the time when we have to replace some existing line and put the new block of the memory, then the previous data will be gone and whatever changes has been made by the processor, that also will be gone. Means you will lose the true copy of the data. So this situation has to be, how to handle this situation. So first, and in case of the multiple CPUs, multiple processors are there. Nowadays the multiple processor systems are there. They can have the individual copies of the caches. Each processor have its own cache. Let us say L1 cache is CPU 1 is there, multiple CPU. It has its own L1 cache. CPU 1, then CPU 2 have L2 cache, L1 cache, and CPU 3 have its own L1 cache, and they are connected via the system bus to the L2 cache and then the main memory. So, each processor have its own cache, and now this data from this cache during the processing or during the execution, this data, some data can be modified as well. It writes the new copy of that data, and now let us say one data which is there in L1 cache of CPU 1 and CPU 2 and CPU 3, all three are sharing that data, they have the individual copy of this data, and now each one is modifying, one of the processor has modified this data, now it should reflect to other processor as well for the further execution. Otherwise this the calculation or the calculation which is currently performed by these processors will be wrong, because other processor will use the wrong copy of that data which is already modified by some other processor. So, this has to be handled. So, for that, so let us say one possible solution for this particular problem is, whenever a cache data, a data by the processor is modified, that has to be immediately reported to the main memory. So, the consistency can be maintained. If some data is processor read took fetch from the cache memory and it is during the execution it is modified, then this modification can be immediately reflected to the cache memory, main memory as well. Means you write in the cache memory and this one write has to be happen to the main memory as well for the same data. Then this consistency can be maintained. In this case, if the multiple processor system is there, so in the case of multiple processor, each processor have to monitor the main memory traffic to keep its own local cache copy up to date. Because as I said, if the two processors are there, one processor is modifying some data. So, as per this write policy, that is called as a write through policy, whenever data is modified, immediately it has to report to the main memory, means main memory write also has to happen. So, if other processor is monitoring, okay, this data for which I have also one copy is modified by other processor, so it will understood from this traffic from processor to main memory via bus, it will monitor and then it will make its own copy as a stale copy of the data. So, that means we need to some information we need to store in the cache line itself that indicates that this is the invalid copy of the data. Earlier it was valid and now it is invalid copy of the data. So, for that we have the valid bit is there already. So, data part is there in each line, data is there, depends upon the block size, then the tag information depends upon the size difference between the cache memory and the main memory, and finally one valid bit is there that says that okay, whether the currently at this line cache line have the valid copy of the data or invalid copy of the data. Now, what is the implication of this? Implication of this write policy. So, implication of this policy is there is a lot of traffic between the main memory and the cache memory, and the main memory and cache memory is connected via the system bus. So, there is a lot of traffic over the system bus, and we know that the system bus there is a lot of other devices are also connected, and it is a shared medium. So, this computation will be more and the delays will be incurred, because every module has to get access first the bus and then it can use the buses. So, now competitors are more and the more activity is going on. So, it can delay the processes. Maybe some devices or some modules will get the buses with some delay. If this traffic can be reduced, can this traffic can be reduced further? So, for that we need to think it. Now, other thing is when another drawback which I can say is, let us say one data is taken from the main memory to the cache memory, and during its period in the cache memory it is modified, let us say 5 times. every time when its copy is modified or copy is changed, this data's copy is changed, one write operation is done in main memory as well. So, for the one data we did 5 times changes, let us say for example. Is it possible that okay, we can make the changes only one time when this data finally has to be removed from the cache line. So, this is another policy. It says update initially should be made in the cache memory only. So, if I am updating data, that has to be keep track as well, that okay, this particular cache line is updated after taking from the main memory. So, now we need one more bit information is to be added to the cache line. So, now I can say this is the final picture of my cache line. What are the fields are there in the cache line? So, data is there, no doubt, tag is there, tag bits will be stored along with the cache line, valid bit is there, 1 bit information, this is a 1 bit and these are the tag and data is a multiple bit, and now one is called as a dirty bit or modified bit or update bit, whatever. So, this dirty bit indicates if the d equals to 1, let us say, now I say the data is modified after bringing from the main memory. If d equals to 0, then data is not modified, it has the same copy as it was taken from the main memory. So, now once the data is modified in the cache memory, this dirty bit will indicate okay, d equals to 1 for that particular block of the data stored in one of the cache line. Now, when this block is to be replaced, because when the cache line, all the cache lines are filled and as per the mapping function, let us say the new block which is referenced by the processor is mapping to one of the existing lines, existing filled lines, then the earlier data has to be removed and the new data has to be put. So, before putting this new data, first it will check whether the dirty bit of this particular block or line is set or not. If it is set, means the data is modified after bringing from the to the cache memory. So, first the changes has to reflect into the main memory. So, first the old data, previous data is to be write to the main memory, and then the new copy of the data has to be, then only the overwrite can be done. Otherwise, if I without writing to the main memory, if we do the overwrite, then the information of that particular data or latest value of that data we will lose. So, this is the way how. So, now this write policy, this is called as a write back policy, means whenever you have to replace the cache line, then only you do. Now, during its span of time in the cache memory, that particular data is modified, let us say 5 times or 10 times. So, there is no write penalty every time. We do not have to write in the main memory, only one time has to be write when we are removing that particular data from the cache memory. So, the traffic on the system bus can be reduced. Is there any implication of this write policy? Because the time period between the data is modified, or you can say the inconsistent data between the main memory and cache memory, that inconsistency time period is more in this case, because let us say data is modified at a t1 and now this data has to remove due to some other, because of the some other block is mapped to this, or we are replacing this data let us say at time t2. So, the t2 minus t1, that time gap is there, and that time gap is, if it is large, then inconsistency, data inconsistency will be there. So, in case of the multiple processors, multiple processor system is there, if they are reading that data from the main memory have the old copy of that data, and that data is already modified by the one of the processor, and it has not been reported back to the main memory also. So, how they will know that okay, this data is this is the old copy of the data in the main memory and fresh copy is available for one of the processor. So, we need some provision for that. So, that is the one thing. So, as I said, other caches get out of syncs, other processor caches will be out of sync. If they have this data, then how they will know, because no immediate write is there now to save the traffic. Another is IO devices must access the main memory. In this case, they should access the main memory through the cache memory, because directly they are accessing the main memory, maybe the data which they are going to access is modified in the cache memory, in one of the cache, then they will end up with reading the wrong value of that particular data. So, all the read of IO should be via the cache memory. If the cache memory says, okay, this is not this is not a modified, this data is not modified, with dirty bit is 0, then it can be taken from the main memory, otherwise it has to be provided by the cache memory. Now, the other parameter which can affect the performance of the cache memory system, that is the relationship between the hit ratio and the cache line size. Cache line size is one of the parameter, through that the cache performance or the hit ratio can affect. So, for that, how the cache operation is there? Whenever any miss occurs, then we take one, not that particular word, because processor generate the word addresses. So, we do not take that particular, only that word into the cache memory. A block of words or some adjacent words are also transferred or retrieved from the main memory to the cache memory. So, that is a one block, and block size can be, let us say, 32 bytes or 64 bytes and so on. So, now we are trying to understand here what is the implication of the size, the amount of data or the surrounding data which we are transferring for each cache miss event. Initially, I can say that if one miss is there, let us say, and I am bringing some 500 bytes of the data in the cache, means my block size is 500 bytes. Similarly, the line size also 500 bytes. Definitely, as per the locality of reference, the hit ratio should be improved, because now next so many references may be definitely as per the locality of reference concept that belongs to these 500 bytes. I brought some 500 bytes nearer to that word address that is referenced by the processor and was not there in the cache memory. So, the first impression it gives me that the hit ratio will be definitely improved if I am increasing the line size, initially I can say, and that is due to principle of locality. If you further increase that line size or block size, the hit ratio will be decrease. Up to some level of the block size, the hit ratio will be improved, because as per the locality of reference you are bringing surrounding data immediately, and the next few references or chances are there that will be available in that range of the data or range of addresses you brought into the cache memory. But later if you increase more, then hit ratio can decrease. Why? You think the other aspect as well. Once the complete cache is filled by, because if block size is increased for a given cache size, the number of lines will be decreased. I am repeating again, for a given cache size, if the block size is increased, then the number of lines, block size or line size are same. So, if the block size or I say the line size is increased, then the number of lines which can be there in the cache memory, that will be decreased. So, all lines are filled, and then you have to remove some data for to accommodate the new block. So, in this case the probability of using the newly fetched information becomes less than the probability of reusing the replaced, because for one miss you bring lot of data and this data is not completely utilized before that you removed it, because your chunk size is large. So, your number of cache lines are less, so all lines are filled, then you have to remove one of the chunk, and chunk your chunk size is large. So, that is why it is not completely utilized before that you are removing. So, later maybe it is required again. If your block size is less, then the number of lines will be more, you can accommodate the different locality of reference data from the different locality of reference, and some data you are bringing. So, the chances that okay, this data will be utilized will be more before it has to remove from the cache memory. So, as I said, the larger blocks, they reduce the number of blocks that fit in the cache. Data will be overwritten shortly after being fetched, and each additional word is less local, so the less likely to be needed. So, now there is no as such definitive size of what should be the cache block size. There is no definitive calculation for that. Again, it depends upon the locality of reference of each program. Every program have the different level of the locality of reference in terms of the amount of data which can be accessed in the nearby references by the processor. But typically the value which is used for the associativity, that is 8 to 64 bytes, that quite reasonable. Now the next thing is, what will be the if so far we talk about one processor is there and then one cache memory level is there and then the main memory, two level memory system. If we increase the number of levels of the cache memory, cache level memory 1, level 1, level 2, level 3, what will be the impact? So, I have one on chip cache memory, because as per the technology advancement, providing cache memory on the chip is also possible now. So, one memory in processor's chip available, another memory cache memory level can be outside the processor, that is a off chip cache, and then the main memory. So, that two level of caches and then the main memory. So, ultimately 3 levels are there. Will it be a better option compared to only one off chip cache and then the main memory? The answer is yes. Why? In case of the two level, let us say only one off chip cache memory is there, data is not available in the cache, then it has to be bring from the main memory and it will take more time. In case of the two levels of the cache memories are there, L1 and L2. L1 is subset of L2, L2 is subset of main memory. So, some data from main memory to L2 cache level it is put, and from L2 some of L2 data is available, is there in the L1. In terms of the sizes, L1 size is less than L2, is less than main memory. So, now in this case this is on chip. So, if this L1 data is not the data referenced by the processor is not available in the L1, then in this case it will go to check L2. L2 access time is less than main memory and more than the L1 access time. So, in case of the simple two level memory system, L1 it is not available, it will go to the main memory, but in this case from L1 it will go to the L2. If data is available from L2, then it can be provided fast compared to get the data from the main memory. So, that is why multiple cache level definitely improve the performance in terms of the average access time will be so multiple access time, multiple cache memory improve the performance in terms of the reducing the average access time of the data fetched by the processor. So, the answer for will more than one level of the cache memory will improve the performance? The answer is yes. But the simplest organization is the two level cache on chip, that is L1 and the external cache. One is available in the processor itself, other is outside the processor. In many cache designs, for an off chip cache a separate bus is used. Not the off chip cache is accessed by the processor, not by the system bus. It is accessed by the separate dedicated bus like this. Processor is there, on chip L1 is there, I am writing here, on chip L1 is there, then this is L2, and then L2 is connected via system bus, and the system bus, this is a main memory is there. So, this is the bus I am talking here, this is a dedicated bus, separate bus is used communication between the processor and the L2 cache memory. Nowadays L1, L2 two caches are available in the chip itself. So a third cache can be introduced, third level of the cache can be introduced, or it is already been introduced, that is L3. So in today's system we have the 3 level of the caches. 2 levels are available in the chip itself and third is outside the chip. And this happens due to the advancement in the technology. More transistors can be put in the chip through the integrated circuit design technology. So now, as I said, that the L3 of chip cache is also available. So 3 levels are there, and then you have the main memory, and the relationship is the same. L1 size is less than L2 size is less than L3 size, and then finally the main memory is there. Now look at how this multiple or multi-level cache performance is there. What is the relationship between the sizes, about the sizes of L1, L2 and L3? So if you look at the size, here the hit ratio is given and the x-axis shows me the size of the cache, and that is the L2 cache size. And so for the curve for L1 equals to, let us say first I will take L1 equals to 8K, 8 kilobyte is a size. So for 8K size this curve is there. You can observe from this graph that we are getting steep. Here we are getting a steep for this curve, and that is equivalent to for 16K. For 16K I am getting a steep here. So this is 32K of L2. So L2 equals to 32K and L1 equals to 16K. That is the relationship. Here the steep in the hit ratio I am getting, means the hit ratio is better hit ratio I am getting at this point. Similarly for L1 equals to 8K, steep I am getting at this point, somewhere this point. So here the L2 size is 16K and L1 anyway it is 8K. So what is the relationship? Means hit ratio is the performance parameter. Now what is the relationship? Relationship is if L2 size is double the L1 size, then the better hit ratio can be get. So that has been observed from the practically or through the experiment, this relationship has been found. So usually L2 cache size is double the L1 cache size. Now next is the cache we can have a different cache for the data and different cache for the instructions, because usually processor requires instructions and data both to execute the program. So it can be possible that okay we have the different caches, or it can be possible that we have the same cache in which the data and the instruction both are there. So in earlier system cache is used for data as well as the instruction, same cache is used, and that is called as a unified cache. Now we have the separate caches for the data and instructions, and that is called as a split cache. What are the advantages of unified cache? In unified cache, the balance between the data and instruction is automatically taken care. Because as per the locality of reference, if more instructions are required, then the more instruction will be automatically fetched. We don't have to take separate we don't have to concern about separately, and if the data is required, then more data will be fetched compared to the instructions. So it is automatically balanced. But in case of split cache, that balance has size, because that depends upon the size. So now I am saying that we are divide the cache into L1 instruction is different, L1 data is different. So what will be the size of L1 for instruction and data? I have to identify find out that okay for instructions maybe I require more instruction compared to the data, and that again depends upon the different programs. So that decision has to take in terms of the sizes of the individual instruction and data cache. Other thing is that this apart from this, the advantage of the split cache is in the parallel instruction execution it is useful. Let us say you this parallel instruction execution means the pipeline processor. In the pipeline processor means multiple instructions execute at the different stages. So let us say one instruction, for one instruction instruction has to be fetched, and for other instruction data has to be fetched, a new instruction has to be fetched and the data has to be fetched. So, data can be fetched from the instruction data cache and instruction can be fetched from the instruction cache. Both are the separate memory, so there is no contention is there. For the single unified cache, at this place contention will be there. So, in the case of parallel processing, the split caches are better than the unified caches. Examples are for the superscalar machines and the Pentium and superscalar machines, Pentium and PowerPC, because they are based on the superscalar pipeline or pipeline processors are there. So, for that it is better. Here I am showing the caches, the internal caches and the external connections for the P3 processor. So, in P3 processor, this is a processor is there, you have separate L1 instruction cache, L2, L1 data cache. So, it is a split cache example. This is split cache, L1 is split and L2 is a unified cache. So, the cache which is nearer to the processor, it is split implemented in P3, and this is far away from the away from the processor, that is L2 cache, that is a unified cache. L1 data and instruction is 16 KB, both are same size, and it is a 4-way associativity. Implemented mapping function is a 4-way associative data cache, and instruction cache is a 2-way set associativity. For L2, it is 512 kilobyte for the P3 processor, and the mapping is done through the 2-way set associativity. Now, let us look at some review questions. So, few questions I put for the today's this lecture. For a large block size, hit ratio initially increase and drops later. Why? Second question is, why the multiple level cache system gives better performance than single level cache system? Third question is, how the conflict misses are different from the capacity misses. So, all these answers you can find from this lecture. So, let us summarize what we discussed today in this lecture. I talked about the cache performance measurement, how to measure the cache performance, and what are the parameters that affect the performance of the cache. So, these are the few parameters through that the cache performance can be affected in terms of hit ratio, average access time, and so on. So, thank you very much.